Hey guys, today we are going to have a very interesting topic which is called polarization. Well, we all experience polarization in our life actually. We all know about it. Practically actually, not scientifically. I doubt, well, I have some doubts that you know about scientifically, but let me ask you some question about it. Have you ever questioned yourself why we wear sunglasses? What is the concept behind the sunglasses? Well, some of you will say, Mister, we can see clearly in sunny days, right? That's true. But what is the concept behind the sunglasses? We all use filters in Snapchat and Instagram, but have you ever questioned yourself? What is the concept behind these filters to make the image that we take prettier, clear? I don't think. Do you have any idea why? Well, this all come under the concept of polarization. Can you spot any difference here in this image between the upper half and the lower half? Well, you can see that the upper half, you can see the guy clearly, the head, right, the camera. However, in the lower half, it's not clear. Well, this is all about polarization. Today, I'm going to have some review with you to make you follow up, remember, and we are going to start with concept of polarization, what polarization means, then the methods of polarizations and Malus's law, and then solve some problems about this topic. Let's have a quick review. You know that the waves are either transverse or longitudinal, right? And you know that the transverse waves, the oscillations of the transverse waves, are always perpendicular to the wave direction. What does it mean? Well, if the wave direction, so this is the oscillation. The oscillation is perpendicular to the wave direction, and that is what we call the transverse waves. Unlike the longitudinal waves, the longitudinal waves are oscillating parallel to the wave direction. So the difference between the transverse and the longitudinal waves, the direction of the oscillations. So the transverse are perpendicular and the longitudinal are parallel. Look to this figure. This one is transverse. Why is it transverse? Because the oscillations are perpendicular to the direction of the waves. The direction of the waves is from left to right. Here, the oscillations is exactly parallel to the direction of propagation of the wave. Let's watch this video together.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
So we know now the difference between the transverse and longitudinal waves. We also talked before about the electromagnetic waves, right? And we know that the light is one of the examples of the electromagnetic wave. We know that the electromagnetic waves are transverse waves. Remember, electromagnetic waves are transverse. Okay. Why is it called electromagnetic? Do you have any idea? Well, the name itself is exposed, right? It's very clear. Electro, that means it has electric field, and magnetic means it has magnetic field. Remember that electromagnetic waves are composed of both of them. Are composed of oscillating magnetic and electric field. Remember, this is the most important thing right now. The electric field and magnetic field are all perpendicular to each other, and all of them are perpendicular to the wave direction. So that is what I mean here. See, the three directions represent, well, the black arrow represents the direction of the wave. The red arrow represents the electric field, and the blue arrow represents the magnetic field. All of them, as you can see from this figure, are perpendicular to each other. So all of these fields are perpendicular to each other. Here it's more obvious and it's more clear, I think, right? So the idea here, electromagnetic waves are composed of oscillating magnetic and electric fields, right? And all of them are perpendicular to each other. Okay, let's watch this video together. This is about polarization. So it will give you some idea about what's going on around us. And it will be a very nice start to understand polarization.
This circular polarizer from my camera, it made me wonder, what is polarized light and how the heck can it be circular? First, let me show you what it does. The most important thing it does is remove reflections. It also generally increases the saturation, meaning things look a little bit more colorful, sky looks darker and more blue, and leaves look more green. See, if I twist the polarizer, I can remove the reflections from this river. It does that by polarizing the light.
Well, we had this introductory video about polarization. I think it's more clear for you what polarization does, right? Well, you could see that the images are polarized, and polarized here means to make the image look prettier, maybe. We can say also to look more clear for you, so you can see clear, right? And you could see that on the lake, right? Like you could see the fish after you adjust the lens, you could see the fish clear, right? But before, with your eyes, you couldn't do that. So that is all under the polarization concept, actually. Well, what do we mean by polarization? Okay, basically polarization is a Greek word. It comes from this Greek word which is polos. So polos is the origin of polarization, and it means orientation. So polarization means orientation. Only transverse waves are polarized. Remember, only transverse waves are polarized. We are going to discuss about why the transverse only. That means the longitudinal waves are not polarized. So the polarization concept is not for longitudinal waves. Be careful about this small hint. When a transverse wave is polarized, that means it only oscillates in one fixed plane perpendicular to the wave direction. It seems like confusing, right? Yes, I think so. It seems confusing. Yeah, when you read it for the first time, it seems confusing. However, I'm gonna explain for you right now. Look to the following notation. This notation, this represents every single line represents an electric field in one plane. So there is a plane here. This is plane, and this plane is of electric field oscillating perpendicular to the direction. Think that this is the direction, okay? And this is the plane, and this is perpendicular, right? You can see it's perpendicular. So all of these planes are perpendicular to this direction of the wave. Imagine like we have also other waves here in between, but I can't do that. I can't keep doing that, right? It's a lot. So I can just represent it by this notation. So in these gaps, we have infinite electric fields, and all of these fields are perpendicular to the wave direction. So the light oscillates along every possible plane. Okay, then what happens? What do we mean by one fixed plane? That means polarization will allow only one plane among all these infinite planes just to pass through. So that means it will cancel out, or it will block all planes and will just make one plane pass through. Okay, I'm saying it's vertically polarized. That means I only allow the vertical plane to pass through. So when this light comes through this vertically polarized or polarizer, it will only allow this one to pass. How about the others? It will block them. So it's like they don't have the license to get through. It will only allow the vertical plan. That is what we mean by polarization. So polarization basically will only allow one of these lines. Let's say I want to have a polarizer of 45 degree. That means this one will be only allowed to pass through because it is 45 degree. So the others will be blocked. So, and that is what we can see here. That is what we mean by polarization. So a transverse wave can be vertically polarized, can be horizontally polarized, or polarized in any direction. It doesn't matter. It can be polarized at 10 degree, 5 degree, 320 degree, whatever. No matter how many degree or which direction you want to polarize. This is unpolarized wave. This is the notation of the unpolarized wave. Remember, the notation of the unpolarized wave in this way. You draw the arrows, you draw 4 arrows crossing at the 0. This is vertically polarized, so that means you will only allow the vertical line to pass through, or the vertical plan to pass through. And this is the horizontal one. So remember, we said the polarization only occurs in the transverse wave. Because the longitudinal waves oscillate parallel to the wave direction. Well, remember, we just mentioned about this here. They all oscillate perpendicular to the wave direction. So if they oscillate in the same direction, what is the point? There's nothing will pass through, right? So that's why the polarization only occurs in the transverse waves. And after knowing about polarization and having some idea about it, let me introduce this video to you, which is about polarization is in 3D animation. I hope it will make it more clear for you. So this is light, and the light which is emitted from the bulb is unpolarized. So the light is unpolarized. This is filter, or we can call it polarizer. As you can see, there are some gaps, and these gaps are horizontal, and that means it will only allow the horizontal lines or planes to pass through, and it will block the other planes. So this is unpolarized light, this is the polarized light, and this polarized light is due to this filter or polarizing filter. So the polarizers or polarizing filters are only allowing the light to pass through in one direction or in one plane. Okay, let's move on and talk about the methods of polarization. We know, or from what we have seen so far, from the videos and from the images we see, that the polarization basically controlled the light intensity, right? We saw that the intensity was, different, right? It also controlled the saturation. It also controlled the reflection which is coming off the surface, such as the water surface. And what it does in the sunglasses is that it reduces the glare, and that's why we don't feel harm in our eyes when we are using the sunglasses. The polarization methods are composed of two methods. First of all is polarizing filters, and we just talk about it right now, right? We just talk about it. It's also called a polarizer. So polarizing filters are called polarizers. It only allows one plane to pass through, and it will block all other planes. Or it will allow one axis to pass through, to get through, and then block the others. You could see that in the previous video, right? Let's have this example. This is a polarizer. This is a polarizer, as you can see. This is unpolarized light. When it gets through this polarizer, what do you expect? What do you expect? I expect that the only plane or axis that will get through this polarizer will be this horizontal one, right? This is the only one will get through and will pass through. The others will be blocked. This is one of the examples, the lens of the cameras, right? Can you see the difference? Well, if you look here, it's not clear, right? However, when you look at the lens, the camera lens, it becomes clear, right? You can control the quality and the camera image to see clear. What else we have? This one, the light beam. This unpolarized light, you can see this polarizer are having vertical gaps, right? So that means it will only allow the vertical axis to pass through, and it will block all other axes. Let's move on. What is the other method? The reflection of the smooth surface, such as the water surface. So reflection from the surface, such as the water surface. Well, what happened exactly? When this polarized light reflects from the smooth surface, such as the water surface, it is polarized. It is polarized because of the water surface. Well, if the water surface is horizontal, as this example we have, I'm expecting this light when it comes here, the only one will reflect will be this horizontal one. The others will be blocked, but the horizontal one is the only one which will be reflected back. Focus about this. So, because the surface of the water is horizontal, it only allows the horizontal. It's like a polarizer here. This surface of the water surface is like a polarizer here. Okay, did you get it? So this polarizer is horizontal, so it will only allow the horizontal axis to be reflected and the others will be blocked. Let's talk about the Malus law. Well, when an unpolarized light passes through a polarizer, what do we expect? Well, based on what we know, it only will allow one axis to pass through, right? Or one plane, right? Which is parallel to the polarized axis, right? One more thing is also occurring here. The intensity of the light is reduced by 1/2 after the polarizer. So here in this example, the intensity of the light, this unpolarized light, let's say it is 1. So it is 1 watt per meter square. When it gets through this polarizer, well, first of all, this is a vertical polarizer, right? Because the transmission axis is vertical, right? Well, nice. I'm expecting the only one will get through is the vertical axis because it is parallel to this transmission axis, right? And this is for the first line. It will only allow one plane, and this is what happens here, right? Vertically polarized light. The others are blocked out, right? Okay, the other thing, the intensity of the light itself is being reduced to 1/2. That means if this intensity is 1 watt per meter square, this one will be 1/2 watt per meter square. Remember, if the intensity is I, this will be I over 2. So it is always reduced by 1/2 by polarizers or due to polarization. Okay, nice. What else we have? We actually, in this process, we use another polarizer. And this polarizer, we call it analyzer. So we have polarizer and we have analyzer. What is the difference between both of them? Well, there's no difference. Both of them are same. They are all polarizing filters. But the function of each is different. The function of the polarizer is to produce polarized light. Let's say produce vertically polarized light or horizontally polarized light or whatever the angle that you choose. However, the analyzer is used to make sure that the light has been polarized. So it is like to confirm whether it is polarized or not. So both of them are polarizing filters. There's no difference. So don't be confused. If the both analyzed and polarized have the same orientation, that means, let's say both are vertical, nothing will same, the light intensity remain the same. So let's look at this figure. Well, we almost have the same figure, right? We just talk about this. This is vertical. This is the polarizer. Well, when it gets through, the vertical axis will pass through, the others will be blocked out. This is the analyzer. It's exactly like the polarizer. It's just different names as we mentioned, right? But they are the same. They are polarizers. Well, if they are both are verticals, like this is vertical, well, the intensity will remain the same. So the light intensity remain the same. However, if the transmission axis of the analyzer was different, it wasn't the same as the polarizer, here the Malus law comes into action. And we need to use the following formula to calculate the light intensity after the analyzer. This theta is the angle between the transmission axis of the polarizer and the transmission axis of the analyzer. So this is the angle between the two transmission axes. What does it mean? Let me show you. Let's say this is vertically polarized, okay? And let's say this is the analyzer. This is the analyzer, okay? Well, when I put this analyzer, let's say I draw it here, this is the angle theta. So this is the angle that I need to calculate, which is mean by this. This is the angle between the polarized or the transmission axis of the polarizer and the analyzer. So this is the angle, okay? Okay, now let's start with some problems to solve different problems about this topic. Unpolarized light has an intensity of 100 watt per meter square. It passes through a vertical polarizer. Well, vertical polarizer means it will only allow the vertical axis to pass through. And then it passed through analyzer at an angle of rotation with respect to polarizer at these three different angles. What is the intensity of the light leaving the analyzer? Well, this is the analyzer. This is the polarizer, right? So this is the polarizer, right? And this is the analyzer. We have light here. The intensity of the light here is 100 watts per meter square. Well, this light, when it passes through the polarizer, first of all, we know when it passes through a polarizer, it will only allow the axis of the polarizer to pass through. Plus, this intensity will be halved after the polarizer. So I am expecting it will be 50 watt per meter square here. Well, now, what do you expect for the intensity here by the analyzer? If both of them have the same orientation, the transmission axes are same, well, I'm expecting the intensity will be same. Okay, let's try to solve it together. So when the angle is equal to 0, here the angle is equal to 45. Here the angle is equal to 90 degrees. Okay, we use the formula. What is our formula? I, the intensity here after the analyzer, equal to the I dot cosine square theta. So the angle is 0. what do we mean by the angle is zero? That the rotation axis between the polarized analyzer is same. So basically that means cosine 0 is 1, because cosine 0 is 1, right? Because the axes are same. They are identical. So the I will equal to I naught, which is basically, how much was I here? It was 50, right? So it's C, 50 watt per meter square. Okay, when the angle is 45, what do we expect? Let's use the formula. I is equal to I naught cosine square theta. This theta is 45 degree. So it will equal to I naught. The intensity of the light which enters the analyzer is 50, right? Cosine 45 is 1 over square root 2. To the power of 2, it will be 1 over 2. So it will be 25 watt per meter square. Okay, when the angle is 90, so this means if this is the polarizer axis, and this will be the analyzer. When the angle is 90, like this one, that means cosine 90 is 0. Think about it. If this was 90 degree, so if we have the light which is polarized already, so this is polarized, vertical polarized light, enter to this filter, what do you expect? It will not pass through, right? It will not pass through, right? It will be blocked here. So I'm expecting, by definition, by our understanding, that the intensity is 0. Can we prove it mathematically? Yes. Cosine 90 is 0. That means I is 0. Okay, is it clear? Is it clear how to use the Malus law? Okay, let's move on. Okay, let's move on to the second problem we have. The sunglasses are a common real-world example of polarization. They are meant to reduce glare. Explain by sketching. Okay, nice. This is the sun, right? The sun is emitting unpolarized light. This unpolarized light is going to the surface. Well, nice. This is the surface. Let's assume this is the water surface. Okay, this is the water surface. Remember that. Don't forget to draw the normal line, and you know that the incident angle is equal to the reflected angle. Anyway, what do you expect? This surface is acting as polarizer, and it's horizontal surface, right? So I'm expecting that the only axis that will reflect it will be the horizontal axis. So the only axis will be horizontal axis, right? Okay, nice. So the others will be blocked by the water surface. Well, do you expect when we design the sunglasses, should we make it like horizontal like this or vertical? If it is horizontal, let's assume make it horizontal. That means this will pass through. This horizontally, the horizontally polarized horizontal polarized light will pass through the sunglasses. So what is the use of the sunglasses? The main use of the sunglasses is to reduce the glare, right? So I'm expecting we're gonna make it like a vertical line in this way. So we are going to make the filters and the sunglasses vertically or vertical polarized, because this horizontally polarized light, when they come here, they will be cut out or blocked, right? They will be blocked by these vertical polarizers, right? They will not be allowed to enter. And that leads to reduce the glare. Did you get it? And leads to increase the contrast. So this is why most of the sunglasses are vertically or have vertical polarizers. Okay, so the idea here is to reduce the glare. Let's move on. Okay, problem number 3, our final problem today. Polarized light leaves a polarizer with the angle of transmission of 90. So we have basically vertical polarizer. The polarized light has an intensity of 10 watt per meter square. So the intensity of the polarized light is 10 watt per meter square. It impacts an analyzer and it leaves with intensity of 6 watt per meter square. Well, after reading these two statements, we have two information. I have this. This is our I node, and this is our I, because this is the light, the polarized light, after leaving the analyzer, right? We know it, right? And we know the light that enters the analyzer, which is the I node. Okay, what is his question here? The angle. He wants to know the angle with respect to the polarizer. Well, we know that the light is polarized, we know it's vertical, and we know that the I node, based on the givens, is 10 watt per meter square, right? And we know the I is 6 watt per meter square. Our question is, what's the angle of the polarizer? What's the angle of the filter? Is it like this? Is it in this way? Well, we need to figure out the angle with respect to the polarizer. We need to figure out this theta. Okay, how to solve this problem? How can we approach it? First step we need to do is write the formula. Our formula is I is equal to I naught cosine square theta. Well, don't forget, because most of you forget the square. Don't forget the square. It's also cosine square. Our target and objective here is to find the theta, the angle. So we need to find the cosine theta. Okay, do we have I? Yes, we have I. Do we have I naught? Yes. So we only left with one unknown. Okay, we just substitute the values. I is 6, I naught is 10, and cosine square theta. Nice, let's continue. So cosine square theta is basically 0.6, right? Because we divide both sides by 10. Then we take the square root. The square root of cosine square theta is just cosine theta, right? And is 0.6 under the square root. How to find theta? We basically take the inverse, the cosine inverse. So the theta is cosine inverse of square root 0.6, and using the calculator, the answer is 39.23 degree. How can we double check if this answer is true or not? Well, anyway, you can double check. You plug. See, you can try to find out I by using the formula. So we need to find out I. Let's say I is 6 here, right? Okay, let's make sure the answer we get is 6. So when we do this, I naught is 10, right? We got the angle is 39. So cosine square 39.23. When you do it with the calculator, is almost 6 watt per meter square. This is to double check. We're done with the lesson. See you guys next lesson. Bye bye.